So, in this week we shall be starting our discussion by looking at how we can create a pipelined version of the MIPS 32 data path. You see, earlier we have seen how we can have a non-pipelined data path for the MIPS 32 instruction set architecture, and we have seen because of the simplicity of the instruction set, because of the regularity, because of the simple instruction encoding, the required hardware was very simple. You need very simple hardware in the data path with very regular interconnections or means interactions between the successive steps. So, if you recall, we have seen that there are 5 steps overall to execute an instruction in the MIPS 32: instruction fetch, instruction decode, execute, memory operation and write back. So, we start from there and we just initiate our discussion for this lecture. We shall be exploring the pipelining of the MIPS 32 data path. So, let us look at the basic requirements first. See, we have seen the non-pipelined data path of the MIPS 32. Let us now understand, if I want to do pipelining, what are the basic requirements? The first requirement of course is we should be able to start a new instruction every clock cycle. See, when we talk about an instruction pipelining, we are saying that instructions are being pipelined. We are feeding the instructions to a pipeline one by one. So, instructions are flowing through the pipeline stages one by one and they are getting executed. So, in the ideal case, I would expect that one instruction would be completing every cycle. That is the beauty of the pipeline, right? So, means once the pipeline is full, we are expected to get one output every clock, right. So, because we are getting one instruction completed every cycle, we should also be able to start a new instruction every cycle, right. This is one requirement. And earlier the 5 steps that we had mentioned, these 5 steps will become a pipeline stage. These 5 steps will become 5 pipeline stages, right. This is another modification we would be doing, and the stages will be such that of course, they must be finished within one clock cycle, because naturally for the pipeline operations to be done in a smooth way. So, your clock period must be chosen to be large enough such that every stage execution must be finished by that time. Okay. So, this is a mandatory requirement. Your clock cycle time must be large enough such that every stage should finish their executions. Now, there are complications that will come in, we shall see. See executions of several instructions will be overlapped now, right, because now we have this IF, ID, EX, MEM and WB as the stages. So, when one instruction is an ID, next instruction will try to come into IF and so on. So, we must ensure that there is no conflict of any sort during the execution of these instructions. Now, we shall also see that there will be conflicts, but the analysis and some solutions to avoid them become quite easy because of the simplicity of the MIPS 32 RISC instruction set. So, we shall be discussing these issues in some detail subsequently. Okay. Fine. Let us see this. This is our non-pipelined MIPS 32 data path. I am showing it like this. So, where all these 5 steps are all together. Let us assume that the time taken by this entire thing is 5t. So, every instruction it comes, it requires a time 5t, it finishes, then the next one comes. So, if there are n instructions, the total time will be clearly 5t multiplied by n. This is the non-pipelined version. Now, for the pipeline version, we do something like this. We break these 5 steps into 5 stages and we insert latches between stages. So, let us assume that each of these stages take time t and latches have a delay of delta. So, we have already seen that how we can analyze a pipeline for its throughput and its execution performance. So, you can similarly say that for n instructions, what will be the total time? 4 clock cycles will be required to fill the pipe, and after that I will be getting one output every clock cycle. So, the total number of clock cycles required will be 4 plus n. And what is the clock cycle time? It must be at least equal to t plus the latch delay delta. Now, if t is large as compared to delta, if we ignore this delta, this becomes approximately equal to 4 plus n into capital T. So, ideal speed up will be 5tn divided by 4 plus n into t. That means, it becomes like this, 5tn divided by 4 plus n multiplied by t. Now, this t cancels out. So, I have 5n by 4 plus n. If I write it like this, 5 divided by 4 by n plus 1. So, as n becomes large, let us say as n tends to infinity, 4 by n will tend to 0. So, this value will be approximately equal to 5 divided by 1. So, this will be my ideal speed up as n becomes large. So, number of stages is 5, my ideal speed up is also equal to 5, just what happens in a pipeline. Okay? Speed up will be equal to the number of stages. So, your ideal speed up will be equal to 5 when n is large. But as we will see later, that things are not that rosy in an instruction pipeline. There will be various kinds of conflicts that will appear. So, speed up will be significantly less than 5. Okay? This we will see slowly. Let us see how the pipeline works. So, I am showing the time steps or clock cycles out here, and let us say instructions are coming one by one. Let us say instruction I plus 1, I plus 2, I plus 3, like this. So, in clock cycle 1, the first instruction I enters the instruction fetch stage. That means, the instruction is fetched. So, after it is fetched, it goes to the decode stage in step 2. So, while it is being decoded, the next instruction can be fetched. So, there is some overlap. So, after this is done, first instruction will go to the execute phase, second instruction to the decode phase, and third instruction can go into the fetch. So, in this way, after 4 steps, the pipe is full and all 4 there are means I mean you can say these instructions are already entered. Now, this way it will go on. Okay? So, the first instruction will finish here, second instruction will finish here, third instruction will finish like this. So, it is after time step 5 instruction I will finish, then time step 6 instruction I plus 1 will finish, time step 7 I plus 2 will finish, and time step 8 I plus 3 will finish. So, as I said, so after the initial delay for the pipe to get filled up, in the ideal case you will be getting one instruction completion every clock cycle. That is the beauty of pipelining. Okay? Fine. Now, you can see that it is not that simple, there can be various kinds of conflicts. So, in this diagram now I am showing two kinds of conflicts. First is between IF and MEM, which is shown in red. Suppose the first instruction was a load or store kind of instructions. Load and store means during the MEM stage it will be accessing memory, it will be reading or writing some data. But at the same time instruction I plus 3 is also trying to read from memory, it is doing an instruction fetch. So, there is a conflict for memory, both instruction I and I plus 3 are trying to access memory at the same time, right. Now, of course, for this particular cases we can suggest a solution that, well, let us use separate instruction and data cache. See, now you can find a logic why people actually use separate means L1 caches for instruction and data. This is the logic actually why it is required. So, if we do that, then this IF will be using the instruction cache and MEM will be using the data cache. So, the conflict which was there is apparently removed or avoided. Okay. Similarly, there is another conflict here. Suppose first instruction is a register type of instruction, let us say add. So, after everything is done, it will be writing the result into the register in the WB phase. Now, if we recall the micro operations that we have seen earlier for the different stages, you will remember that in the ID phase the register operands are prefetched. So, again here marked in blue there is a conflict in time cycle 5. The instruction I plus 3 is trying to read from the register bank, instruction I is trying to write into the register. So, this is also some kind of a conflict. So, what is our solution here? Our solution is, means here we shall be allowing in some way, we shall be seeing that later, both read and write to continue in the same clock cycle for the registers. We can read from the registers, also you can write into the register in the same clock cycle. Well, means you may think that this is a little funny, because how you can write or read from a particular register in the same cycle, but we will see that it is possible to do that, right. Okay. Now, coming back to the advantages of pipeline, which you have means already seen just now, that in the non-pipelined version of the MIPS, the execution time of an instruction is equal to the combined delay of the 5 stages, which you have shown in that example 5t. But in the pipeline version, in the ideal case, once the pipeline has become full, one instruction gets executed after every time t. Of course, we are assuming that all stage delay, this should be stage, all stage delays are equal and equal to t, and we are neglecting the delays of the latches. But we shall see later that it is not so simple in the practical scenario, because of various conflicts that can arise between instructions which are commonly known as hazards. We cannot achieve this ideal performance, because in the ideal case we have seen that our speed up can approach 5, but because of hazards it can be less than 5. But however, various techniques have been proposed by the designers to improve the performance to the extent possible. We shall be looking at several of the techniques. Okay. Fine. Let us look at some of the observations which we discussed a while back. Let us look at the memory constraint. Earlier, when you had a non-pipelined version of a MIPS processor, what was there? So, an instruction was getting executed in 5 steps, let us say 5t time. So, the total time was 5t, non-pipelined version. There were 5 steps of execution. Let us note them down: instruction fetch, instruction decode, execute, memory and write back. Now, if we consider memory access, in this 5t time there was one memory access here and there can be another memory access here. Of course, all instructions are not load and stores, but in the worst case there will be 2 memory accesses here. So, for the non-pipelined version there will be 2 memory access maximum, I am talking of the maximum, 2 memory accesses in 5 cycles. This is for the non-pipelined case. But for the pipeline case, what happens? Just now we have seen that the instructions will be overlapping, right? Like one instruction will go like this, next instruction will go like this, third instruction will go like this, and so on. Okay. Now, what happens here? Let us show one more, and so on. And so, again the next one will start IF here. Now, what I am saying is that here you see I am talking of the worst case. Here in the worst case, in every cycle there can be potentially 2 memory accesses. Right. Earlier there were 2 memory accesses in 5 cycles, but now for the pipeline version there can be maximum 2 memory accesses in 1 cycle. So, what does that mean? It means simply that my memory bandwidth requirement is increasing 5 times. Earlier the data transfer rate, whatever was there for our memory system, here we are demanding 5 times the bandwidth. Okay. So, this is a big issue. So, this has been summarized here. To support overlapped execution, the peak memory bandwidth must be increased 5 times over that required for non-pipeline version. Means, as I said, that instruction fetch in a pipeline occurs every cycle, and because some other instruction can also access data, there can be maximum 2 memory accesses per clock. So, one solution I have already said that in the level 1 cache we use separate instruction and data caches. Most of the time, because of the locality of reference, data referenced by the CPU will be found in the caches. So, there will be no conflict. One instruction can fetch from I cache, other instruction can read or write from the D cache. but of course, when there is a cache miss, there will be of course a delay that is there. But this is a simple solution, and this explains why we have separate instruction and data caches. The second is that register bank issue. So, we saw earlier, we mentioned that some instruction can read a register bank during ID, some other instruction can write into a register during WB. So, we just made a loose statement that we shall allow both read and write to happen in the same clock, but how is that really possible? Let us find a solution here. Now, in the ID stage, what we are doing? ID stage, we are prefetching both the register operands, okay, source 1 and source 2. So, this ID requires 2 register reads, and in WB we require means at most 1 register write. So, in a pipeline, our requirement is that in every clock cycle we should support 2 register reads and 1 register writes. So, how we can have 2 register reads? Well, if our register bank has 2 separate read ports, then reading 2 registers parallelly or concurrently is not that much of a problem, but the trouble will be someone is trying to read register R1, but someone else is trying to write into register R1, then what will happen, right. So, simultaneous reading and writing will result in clash if same register is used. Now, here a very simple trick is used to solve this problem. So, what is done in the MIPS pipeline is that we divide the clock cycle time into 2 parts, 2 halves. Let us say our clock cycle starts from here, leading edge, falling edge, that is our total clock cycle. So, we are saying that in the leading edge of the clock we do all the register writes, and the falling edge of the clock we do all the register reads. Because you see, register access is pretty fast and clock cycle time is pretty long, because all these stage executions must finish by that. So, within that clock cycle time we are dividing into 2 halves. In the first half we are doing the write, in the second half we are doing the read. So, in case that kind of a thing happens, that someone is writing into R1 and some other instruction is reading from R1, then first that write will happen, then that read of that new data will happen. So, the correct data will come in, right. So, what we do is that we perform the write during the first half of the clock cycle and the reads during the second half of the clock cycle. This is the convention we follow. So, the clock cycle is divided into 2 halves, first half we do write, second half we do reads, right. So, our register bank picture will look like this. There will be 2 read ports. So, source register numbers will be fed as a register address 5 bits 5 bits, and the 2 register values will be read out just like reading memory, right. And on the other side there will be a write port which also will specify the register number where to write and also the data that is to be written. As I said, write will happen in the first half of the clock and the 2 reads will happen during the second half of the clock. So, by using this simple convention and this modification to the register bank, we can avoid this conflict also. Okay. Fine. And the third important issue is that, you see, earlier if you recall the micro operations for the non-pipelined MIPS, there in the instruction phase or IF stage we were not incrementing the PC. What we are doing is that we are using a temporary register called NPC. We were storing PC plus 4 into NPC. Later on during the mem stage, we were transferring that NPC into PC if it was not a branch. Okay? That was happening in a non-pipeline version, but now we are doing a pipeline. Can we afford to do that? Because in every clock I need to fetch an instruction. So, my PC should be ready with the address of the next instruction at the end of every clock. So, at the end of every clock in IF itself, I have to increment my PC. If I do not do that, there will be a trouble. So, PC updating has to be done during the IF stage itself, because if you do not do that, you cannot fetch the next instruction in the next clock. I mean, as I said, in the non-pipeline version, this was done in the mem. So, some basic performance issues can be discussed here. So, I am showing the MIPS pipeline 5 stages with the latches. So, register stages or latch stages are inserted, as you know. These are required for correct pipeline operation, because if we do not use these latch stages, then the output of one stage may disturb the input of the next stage, so that the computation can become wrong. And again the clock period has to be chosen suitably, this also discussed earlier, because clock period T will depend on the slowest stage of the pipeline plus also the clock skew and jitter and the setup time of the latches. So, all these times taken together will determine the minimum clock period that will ensure correct operation of the circuit, right, or the maximum clock frequency. Fine. Here let us take an example. So, we consider a 5-stage MIPS pipeline with clock rate of 1 gigahertz, which means 1 nanosecond clock cycle time. Now, in a non-pipelined implementation, let us assume that ALU and branch operations take 4 cycles to finish, while memory operations, because they also need memory access, will take 5 cycles. And also assume that the frequencies of this ALU, branch and memory operations are 50%, 15% and 35% respectively. So, we also have a equivalent pipeline implementation, where because of the register stages, clock skew etc., the clock cycle time, which was 1 gigahertz, is increasing by 0.25 nanosecond. It was 1, it becomes 1.25. So, the question is, what will be the estimated speed up of the pipeline implementation? This is a very simple problem. Let us see. So, for the non-pipeline processor, what we do? We can calculate the average instruction execution time by multiplying the clock cycle time with the average cycles per instruction. Now, clock cycle time, it was 1 gigahertz, that means 1 nanosecond, and average cycle time, you see it was mentioned 50% are ALU, 15% are branch, 35% are memory, and they take 4 cycles, 4 cycles and 5 cycles respectively. So, 0.5 into 4, 0.15 into 4, 0.35 into 5. So, if you calculate, it becomes 4.35. But for the pipeline processor, as I said, that the clock cycle time is slowing down, it becomes 1.25. Now, assuming that there are large number of instructions in this steady state, one instruction gets executed every clock cycle. So, the average instruction execution time will be equal to the clock cycle time, 1.25 nanosecond. So, speed up will be 4.35 divided by 1.25. So, you see this is based on some realistic figures, that our speed up is coming to about 3.48, not exactly 5. Okay. Now, let's have a quick recap on the non-pipelined MIPS 32 micro operations. This we have seen earlier. See, in the instruction fetch in the non-pipelined version, we are doing this. We were fetching the instruction, incrementing the PC, but storing it in NPC. See, NPC to PC was being transferred only during mem, right? This. In ID, we are prefetching the registers. We are also prefetching the immediate data and doing sign extension. In the EX stage, we are doing some arithmetic operation, but depending on the type of instructions, it can vary. For memory, we are just adding this IMM to A to calculate the effective address of the memory. For ALU operation, we simply just operate on A and B, some function. For immediate operation also the similar thing, A some function IMM. But for branch operations, we are calculating the branch target address, and also we are evaluating the branch condition, whether it is a taken branch or non taken branch. A, we are checking A is 0 or non 0. And again during mem operation, if it is a load instruction, we do a memory read. If it is a store instruction, we do a memory write. If it is a branch instruction, we are simply checking the condition. Based on that, we are updating the PC with ALU out or with NPC. But if it is any other instruction, simply PC equal to NPC. So, PC is getting updated much later here. Okay? This is one observation. And in the write back stages, we are storing either the ALU output or for load instruction, the output from the memory into the register. Now, we have also seen that all the things taken together, the data path looks like this. Now, next what we will see is that if I want to make this into a pipeline, what are the changes that are required? What are the modifications I need to do? Okay? Like for example, one immediate thing I can see that this PC is getting modified based on a decision that is taken in the mem stage. So, I cannot wait till that long, because I have to fetch a new instruction every clock cycle. So, I need to increment my PC in the IF stage itself. Okay. So, these are a few things we shall be seeing in our subsequent lectures. Thank you.